Good morning, everyone. Today we're doing Unit 2, Lesson 6, Polynomial Key Features. So in today's note, we're going to look at some key features of polynomial functions that we can identify both from the equation and from a graph. And then when we can identify them from an equation, how can we then do a rough sketch of the polynomial function based on those key features? So one of the key features that we've already looked at in this unit, but we'll discuss again, is our end behavior. So our end behavior talks about what does the y values do as x approaches negative infinity and as x approaches a positive infinity. So we've talked about this in a previous note, that when it's positive in general, we're going up, and when it's negative, it's going down. It depends if we're looking at an odd degree or an even degree, so we'll kind of summarize this chart we have in another note. But first of all, how do we find it? How do we identify it? So identify the degree and the sign on the leading coefficient. If the degree is odd, the end behavior goes in opposite directions. So we saw this with our cubic operation, that the end behavior could either go like this, or the end behaviors could go like this, right? Where it's down to the left, up to the right, or up to the left and down to the right, either one. If it's an even degree, then the end behavior goes in the same direction, either both up or both down. So the end behavior goes in the same direction. So if you think about a parabola, we can either have a parabola that's opening up on both ends, or the parabola could open down on both ends. That's our end behavior. So based on if the degree is even or odd, use the sign on the leading coefficient to determine the end behavior. So that sign on our leading coefficient will tell us if it's negative or positive, and that'll tell us what's going on with our end behavior. So let's just remember, this is a refresher from our previous day's note. So our odd degree polynomials, if they are positive, then as our x is going to negative infinity, our y is going to negative infinity. And if as our x goes to a positive infinity, our y goes to a positive infinity. So similar to a line, similar to a positive sloped line like y equals x. If we're talking about the negative version of this, so as x goes to a negative infinity, y is going to go to a positive infinity, and as x goes to a positive infinity, y is going to go to a negative infinity. So we're going to have y equals negative x. It's going to be similar to a line sloping down. If we look at even degree polynomials, when those are positive, both endpoints are positive. So y is approaching a positive infinity on both endpoints, and that would be similar to our parabola that's positive, like y equals x squared. When our leading coefficient is negative, then both of our endpoints are approaching a negative infinity or pointing down, which is similar to a y equals negative x squared parabola, where the parabola points down. Okay? So another key feature that we can look at is our x-intercepts, which we've been able to find our x-intercepts when we're looking at linear functions or when we're looking at quadratic functions. So remember that your x-intercepts are your points where the function crosses the x-axis. Right, so it's some number and 0 if we were to identify the coordinate of that x-intercept. How do we find it? We've done this with linear and quadratic functions in the past. We're going to set y equal to 0, and then we have to factor to solve. We need to get it into factored form to find those zeros. So a polynomial of n degree has at most n zeros, right? So what that means is a quadratic, so x to the power of 2, at most it's going to have 2 zeros. A cubic, or x to the power of 3 degree, at most is going to have 3 zeros. Okay, and so on. If we looked at higher degree operations, the number of zeros would just match whatever the degree was. Something new we're going to look at today is this idea of multiplicity. So our multiplicity is how many times does a zero appear in a function? So how many times a zero appears in a function? So we'll look at an example of what I mean in a second, but let's just talk about the different multiplicity options. So if the multiplicity is 1, the graph is going to cross the x-axis at that 0. If the multiplicity is 2, the graph kisses or just touches the x-axis at that 0. And finally, if the multiplicity is 3, the graph flattens at the x-axis at that 0. And flattens is the same as tangent, which means it's going to be parallel to the x-axis. And we'll look at examples of all of these. But let's look at an example. So if I had the function f of x equals x minus 3 squared, okay, I could identify my zeros. So my 0 is going to be at x equals 3, and it's going to have a multiplicity of 2. So our multiplicity is how many times does that 0 show up in the function. And this represents our multiplicity. That exponent tells us how many times does that 0 show up in the function. So with a multiplicity of 2. I'm just going to point up to the exponent. So that tells us our multiplicity. So if we were going to draw this, we would plot our 0 at 3, right? We have a positive function, so we know we're opening up and it's quadratic. But at that 0, it's just going to touch the x-axis. It's not going to cross it, so it's just going to touch it. And then we can draw our endpoints based on the fact that we know that our leading coefficient is positive, so it must point up, okay? And it's an even degree polynomial. All right, so that's what it means by touches, not crosses the x-axis. Okay, another key feature that we're going to look at is our y-intercept. So like our x-intercept, our y-intercept is just where the graph crosses the y-axis. And to find our y-intercept, we're going to sub in x equals 0 and then solve for y. The y-intercept is always the constant in a function. So it's always the constant in a function, that number being added at the end or subtracted of a function. Okay, so let's look at some examples. All right, so use the following functions to answer the questions below, and then we'll sketch them just based on those key features we identify from the equation. So first we have f of x equals x cubed minus 10x squared plus 25x. So what can we identify before maybe having to change it from standard form to factored form? So what is the leading coefficient? Well, we have a 1 on our highest degree x there, so our leading coefficient is a positive 1. More importantly, that we recognize it's positive. What is the degree of the function? The highest exponent is a 3, so the degree is 3. Is the highest exponent odd or even? Okay, well the number 3 is odd. So therefore, if we have a positive degree of 3, we should start to recognize what's going to happen with our end behavior, right? We're going to have some kind of cubic, something like that. Because if it's positive, it's down to the left, up to the right, with a degree of 3. So what are the zeros of this function? So in order to identify the zeros, we're going to need to factor the equation. We need to get it into factored form. So if I was to factor this, I'm going to start by common factoring out an x. So I'll be left with x squared minus 10x plus 25. All right, and then looking inside the brackets, I see I have a perfect square trinomial. So that x squared minus 10x plus 25 is going to factor to x minus 5 squared. Okay, so we can pull our zeros out of there. So we have x equals 0. So just so we're clear where those zeros are coming from. So my x equals 0 is that first factor we identified. And then our other factor is going to be setting x minus 5 equal to 0 in solving. So x will equal 5. So we can show that that 0 is coming from this factor here. All right, if we identify our multiplicity, so when we look up in the equation, we can see that we only have an x one time in our equation. So that has a multiplicity of 1, which means it's going to cross the x-axis at that point. Our 5 has a multiplicity of 2, though, right? It occurs 2 times in our function. So that means it's going to kiss the x-axis at that 0. Okay, what is our y-intercept? So our y-intercept can be found by substituting a 0 in for our x, and I'm going to substitute it into the factored form just because it's easier to calculate. All right, so 0 minus 5 is a negative 5, and negative 5 squared is 25. 25 times 0, though, is 0. So our y-intercept is just at 0. Okay, what will the end behavior of the function be? So if we have a positive third-degree function, then if we look back at our table, hopefully we start to remember these, but as x approaches a negative infinity, y is going to approach up negative infinity. And as x approaches a positive infinity, y is going to approach a positive infinity. Okay, so let's plot our zeros first. We know we have a 0 at 0 and a 0 at 5. And we'll just put that that's 5 there. Okay, our end behavior tells us that to the left, we should be going down to the left, right? As x approaches negative infinity, so does y. And on the right side, our end behavior should be going up, something like that. All right, we also know that this is a cubic function, so we should pay attention to how many turning points we're going to have. If it's a cubic function, then we're going to have 2 turning points. Just remember, our turning points are just n minus 1. So we have our y-intercept. At that y-intercept, which is also our 0, we're going to cross the x-axis. So we're going to cross from negative to positive. But at this x-intercept of 5, it's only going to kiss the x-intercept, so it's not going to cross it, it's just going to touch it and come back up. And then those two should meet somewhere so that we have 1, 2 turning points. I just want to point out, for a cubic, we're going to have 2 turning points, okay? Just the 2 there. So that's a rough sketch of a cubic. Let's take a look at the next function. So our next function is g of x equals a negative 6 times x minus 2 times x plus 1 to the power of 3. Pay attention to the fact of those multiplicities so you can kind of think about what's happening with our zeros right at the beginning. So we have this x minus 2 has a power of 1, so really that's just a multiplicity of 1 on that 0, but our x plus 1 has a multiplicity of 3, so that's going to look different on the graph. But let's see what we can identify in factored form. So what is the leading coefficient? Our leading coefficient is a negative 6. And remember, the important piece of that is that it's negative. That'll tell us something about our end behavior. What is the degree of our function? So when we're trying to identify the degree of our function, we have to see how many x's do we have here and what is that total. So here we have an x to the power of 1 and we have an x to the power of 3. So that tells me in total I have x to the power of 4. So my degree of my function is going to be 4. Is the highest degree term even or odd? Well, a 4 is going to be even. So just thinking about our leading coefficient and the fact that it's a degree of 4, right? It's an even degree and it's negative, so that tells me that my endpoints should be going down if it's an even negative function. So what are the zeros? So again, for our zeros, we can just set each factor equal to 0. So x minus 2 equals 0, and x plus 1 equals 0, and then solve for x. So x is going to be 2, and x is going to be negative 1. Now, in terms of the multiplicity on those, if we look at our 2, we already talked about, it has a multiplicity of 1, so it crosses the x-axis at that 0. Our 0, our x-intercept of negative 1, has a multiplicity of 3, so it's going to flatten out. It flattens or is tangent to the x-axis, and we'll look at what that looks like at that point. So what is my y-intercept? So again, for our y-intercept, we can just plug in, oops, that's a g of x, so we can plug in a 0 into our function and see what we get for our y-intercept. So we're going to have 0 minus 2 times 0 plus 1 to the power of 3. So if we were to calculate that, we should find that that equals 12. So our y-intercept is going to be at 12. So what will the end behavior of the function be? So again, let's start by plotting our zeros. So we have a 0 at 2, and we have a 0 at negative 1. Okay, in this case, we also have a y-intercept that's something other than 0. We have a y-intercept up here, let's say y-intercept somewhere up here at 12. So this is 12. All right, so at my zeros, I know my end behavior is going to be down from both of these, right? So from 1 we're pointing down, from 2 we're pointing down. We have to kind of sketch what's going to happen between them though. So at 1, I have a multiplicity of 3, which means my graph is going to flatten. It's going to do something like this. It's going to be tangent to the x-axis, and then it's going to shoot up. We got to make sure we cross that y-intercept. And at my x-intercept of 2, it's going to cross. It's going to fully cross. So it's not going to flatten, it's just going to fully cross at that point, and again, come up and meet or come back down somewhere around there. Okay? So we can see that we have a degree of 4. If we wanted to take a look at that, we can see that it flattens at negative 1 and it crosses at 2. Pause the video at this time and see if you can go through examples 3 and 4 like we did in the table of values on the previous page, identifying everything in the table, and then we will do the sketch together. So just try to fill out the table for 3 and 4. Okay, so here's the filled in solution for number 3. Our leading term is going to be 1x to the power of 4. And the way we identify that is we have to count how many x's do we actually have in here. So in our first bracket we have an x, and second bracket we have an x, in our third bracket we have a negative x squared. So if we combined all those, if we did x times negative x squared, that should equal a positive 1x to the exponent of 4. So that's going to represent our leading term. So our leading term was a 1x to the power of 4, which is positive. Our degree is 4, which is even. So that is where our drawing of our endpoints come in. Our endpoints should both be going up because we have an even polynomial that's positive. Then we list our zeros, which we found above, and discuss what their multiplicity is. And multiplicity is written there in brackets. So if it's a multiplicity of 1, it's going to cross the x-axis at that 0, and if it's a multiplicity of 2, it's just going to touch or kiss the x-axis. We can find our y-intercept by subbing 0 in for x, and when we do, we should get 108 for our y-intercept. And then finally, our end behavior just communicates what we talked about with the y's going up on either end of the function. So let's graph our zeros. So our first 0 is at negative 6. So we'll say negative 6 is somewhere over here. And then we have a 0 at 2 and at 3. So we know our end behavior on either end of our 0, our function is going to be going up to the right, right? Y is going to approach positive infinity. Some other things we know our y-intercept. I know this scale's probably terrible, but we're going to say that this is a negative 108 over here. So we know we have to cross our y-intercept as well. At negative 6, at that 0, the function is going to cross the x-axis, so we should come down. It doesn't need to come back up to the x-axis until our next 0, which is at 2. So at 2, the multiplicity is 1, so again we're going to cross the x-axis and then come back down to 3. And at 3, our multiplicity is 2, which means it just touches the x-axis there and then goes back up. All right, so that's a rough sketch of that function. Let's look at the next one. Our next function, we can easily identify the leading term as 1x to the power of 3, and that 1 is positive. So we have a degree of 3, highest variable is 3, and it's odd, so that will tell us that our endpoints will go down to the left and up to the right. To identify our zeros, though, we are going to need to factor this function. So we start by common factoring out our x, and then we continue to factor using SPF. And then finally we identify our zeros down here at the bottom. So with our zeros, we need to also recognize what's our multiplicity. So our multiplicity is written in brackets. Each one has a multiplicity of 1, so they should all cross our x-axis. Our y-intercept is at 0, and then again, those end behaviors just communicate what we already said about it going down to the left and up to the right. So let's start by plotting our x-intercept. So we have an x-intercept at 0, at -1, and at -2. All right. Our end behavior tells us that at the end of 1, 0, we should be going down to the left, and we should be going up to the right for the other 0. They're all going to cross the x-axis. So at -2, which I'm just going to label these -2, -1, so we remember. At -2, it should cross the x-axis, and then come back down to get your next 0 at -1 and cross the x-axis, and come back up to get your next 0, which is at 0, and cross the x-axis and continue to come up. All right? So now we're going to look at actually looking at a graph and seeing if we can identify the equation from that graph. Okay, so in our first graph here, we can look at what are our zeros. Those zeros will help us at least get the equation into factored form. So we have a 0 at 0, but notice it's only touching. It's only touching the x-axis, it's not crossing it. So that tells me we're going to have a multiplicity of 2. At this 0, at 3, it's crossing it, so that's going to have a multiplicity of 1. So let's just write that we're identifying our multiplicity. Right? So one's going to have a multiplicity of 2, and one's going to have a multiplicity of 1. If we try to think about our leading term, we have to think about what's going on with our end behavior. So if we're up to the right, or sorry, up to the left rather, and down to the right, that should tell us that we're going to have a negative leading coefficient. If we look at whether this is odd or even, well, our end behaviors are going in opposite directions, so that tells me that my function should be odd, because if it's even, then the end behaviors go in the same direction. We can identify our zeros just by looking at our graph. So one of our zeros is 0, and the other one is 3. If we wanted to talk about their multiplicity, we know that 0 just touches, so it has a multiplicity of 2, and at 3 it actually crosses, so it has a multiplicity of 1. And the last thing we can tell is our y-intercept. So our y-intercept crosses at 0. So if we wanted to put this into an operation, we could say f of x, we know that our leading coefficient has to be negative, okay, and then we have 1 0 at 0, and it has a multiplicity of 2. So we're going to have a negative x squared. And then our other 0 is at 3. So that tells me it's going to be in brackets x minus 3 to represent that 0. Okay, so there is a rough equation of that. There might be some other multiples that are in there to scale the equation up or down, but right now we're just looking at what's a possible equation for that graph. So let's look at the next one. So let's again identify our zeros, and then identify their multiplicities. So we have a 0 here at -1, and that just touches. That's just touching the graph. So that tells me it has a multiplicity of 2. This 0 here at +2, that flattens, right? It's flattening, or a tangent at that x-axis. So that tells me we have a multiplicity of 3. So we're just identifying our multiplicity. So I have to decide, do we have an even or a positive or a negative coefficient? So our end behavior is going down to the left and up to the right. So if we think about a line that slopes up to the right, it would have a positive slope. And again, the end behaviors are going in opposite directions, so we have an odd function. Our zeros are at -1 and a +2, and if we put with them their multiplicity, at -1 we have a multiplicity of 2, and at +2 we have a multiplicity of 3. And then finally, our y-intercept we can just see by looking at the graph right there, 1, 2, 3, 4. Our y-intercept is at -4. Okay, so if we're trying to have a function for this, we could say that f of x, now we know it's going to be positive, our factors are going to be at -1, so we're going to have x plus 1, and at x minus 2 for other one. And then we can tag on those multiplicities. So x plus 1 is going to have a multiplicity of 2, and x minus 2 is going to have a multiplicity of 3. If we were to expand and simplify our function, we wouldn't necessarily get a y-intercept of -4 right now, but I don't want to worry so much about that. We just want to get it into a rough equation. We will look at how do we accurately represent this -4 in another lesson. For now, we're just getting our zeros and our multiplicity into an equation. The last part of the note today is we're just going to predict higher degree polynomial functions and then kind of summarize what we've learned today. So if we were going to predict the general shape of a 5th degree curve, remember a 5th degree curve is odd, and we know that odd curves are going to go have opposite end behaviors. One's going to be down and one's going to be up. If we were to look at an even degree curve like the 6th degree, that's an even one, and we know that both endpoints should go in the same direction, whether that's up or down. So if we were talking about a 5th degree, well, we know, like we just said, if we were looking at a positive one, for example, then one end behavior will go down and one will go up, or the other way around. We know that at most, it asks also how many zeros. At most, we're going to have 5 zeros. And then we could also identify our turning points. So remember, our turning points are just n minus 1. So the most turning points we could have would be 4. So let's try to draw what we think would happen. So if we're going up and we come down, that's 1, 2, 3, 4 turning points. And we can count them. 1, 2, 3, 4. So that's what a 5th degree curve might look like. If we were going to do a 6th degree, again, we could say at most for our zeros we could have 6, and our turning points are just going to be 1 less than that. So at most for our turning points we could have 5. So for a 6th degree, we know that our endpoints have to go in the same direction. So let's say we're dealing with a positive one. We'll put them both up. So we need to have them both end behaviors going up, and then we're going to need 5 turning points. So we'll have 1, 2, 3, 4, and 5. Okay, you can count those turning points. 1, 2, 3, 4, 5. So that's a rough sketch of what a 6th degree curve could look like. All right, the rest of this is already filled in for you. We'll just chat about it for a minute to summarize. So after we've kind of gone through this investigation, what can we really tell about all these different polynomial functions? Well, if you have a linear function, and we've seen this in other notes and today, the most x-intercepts you can have is 1, and the least you could have is 0. So if we were going to have, I'm not sure why this is, let's rewrite that x-intercepts there. If you had a horizontal line, you would have 0 x-intercept. They would cross the y-axis but not the x-axis. But if you had a line that sloped up or down, you would cross the x-axis at least once, so 1 x-intercept. All right, and our turning points, again, is just n minus 1. So if our highest degree here is 1, then 1 minus 1 would mean we have 0 turning points. If we look at another type of odd degree one, so if we looked at a cubic, which recall a cubic is any function where the highest exponent is 3, or x to the power of 3, then we could have as many as 3 intercepts or as little as 1 intercept, which the two graphs show here. Okay, it could cross 3 times, or if the graph is moved up or down, it could possibly just cross 1 time, but it does have to cross at least 1 time because your end behaviors are going in opposite directions. In terms of turning points, if our highest degree is, or our highest exponent is 3, then the turning points is just 1 less than that, so our turning points are 2. Quadratic, now we're moving on to even. Remember, an even degree function can have as little as 0 x-intercept or as many as n. Whatever the degree is of that function, that's how many x-intercepts it can have. So for a quadratic, we have a degree of 2, right, and x squared, that's the highest exponent. So we can have as many as 2 x-intercepts. Our turning points will just be 1 less than that, so we'll have turning points of 1. For a quartic function, our highest exponent, or the degree, is 4. So we can have as many as 4 x-intercepts or as little as 0. And our turning points will just be 1 less than 4, so our turning points will be 3. That's it for the note today. Pause and make sure you copy this summary down in your notes.